Okay, welcome to the last talk of the conference at this stage or in this stream. Thank you all for still attending after such a long and eventful day. So my name is Jozef Styrak. I lead a team of machine learning engineers at Seznam. I have a background in big data and machine learning. And as you can see, big data means big bird. So that signifies that I actually mostly work with ML right now. Seznam is a technological and media company, one of the largest in Czech Republic. It provides many successful products for its customers, like maps, TV, email, search engine, web browser, and many, many others. I happen to work for one of the most popular ones among the general public, advertising and personalization. In all seriousness, is the backbone of the Seznam financial model. It's also one of the biggest divisions and also one of the most technologically diverse and interesting. There are few types of advertising. Ones that are significant for our work are the targeted ads, where an advertiser chooses some categories by which he wants to describe his desired audience, and then we want to target his advertisements on these groups of people. Okay. There are machine learning models and pipelines underneath it all, which try to basically guess which people are which category, ranging from age, gender, to interest categories, geolocation, or some that are more difficult to explain. Just to mention some numbers, we have 4 billion web hits daily from 10 and plus million of unique user devices daily, which of course fluctuate on the weather on a given day or whether the parliamentary elections are happening in the country. Which leads us to the agenda of this talk. I would like to talk to you about our journey with machine learning from our humble beginnings. With the challenges of it, we're going to mention some tools or some concepts that help us make it better, and we can look at it as a whole picture. How could it be done in a better way? Let's start with how your first model may look like. In our case, a good example is user classification into age groups. It's one of the most common targetings, and also the prediction from the models can be used in various other use cases, like some sort of recommendation system or some sort of parental control or media content control. So how the implementation may look like? Usually it starts with the data scientist who explores the data. Some of the data sources are quite reliable and some not so much, some are quite obscure. He explores also the space of possible algorithms, which patterns he can extract and how from the data. And in the end, he takes or creates some features, uses an algorithm to implement and basically create a model artifact. And with some guidelines, he provides it to the developers, and he moves on to another project. So the developer takes the model artifact with those guidelines and decides to package it. In this case, for example, like some sort of service that provides predictions, and the user can call it and get the predictions they want. He also builds a inference pipeline that tries to mimic the data transformation used in training and mimic them in the language he chose for the implementation of the inference pipeline. On top of it, he adds basic monitoring that is used from other microservices. And then the model lives on. Okay, after a couple of months, it may happen that someone notices something wrong with the data. In a better case, it could be a product owner or you who notices that the graph and dashboards do not look quite okay. For example, the distributions of age groups is shifting. But in a worst case scenario, there may be a customer complaining that his ads are shown to the people he didn't really want to show them to. Or it may be something quite trivial, like you need to upgrade some dependency, some packages are being obsolete. Like the bottom line is that you need to do a change. And you need to retrain the model, adjust it somehow. This is surely fine. There can't be anything difficult with it. It's going to be a quick fix. Unfortunately, a lot of time it isn't. So what can go wrong? Depending on your implementation, there may be problems, like quite basic ones. You may not be able to find a place where to run the original Jupyter notebook, or the code dependencies may be obsolete. There may be some problem with the build. It may be difficult to find the original experiment results, so you cannot really compare the previous model with your new one. Or it can be more production-based. For example, the model may behave in the training quite okay, the offline metrics look okay, but in the production it performs poorly. It all takes longer than you expected, and the project is late, you cannot work on other stuff, and so on. So what can we do about it? Like most of you will think that there's really nothing new about it. Those are the same problems in other software engineering systems. And mostly you are right. The ML code part is like a small piece of the whole. Like many other parts are inspired, or like is the stuff that you can also encounter in other software engineering systems. It can be inspired from data engineering, like all the stuff that you do to the data, ETL pipelines, the monitoring of them, stuff like that. But also all of backend services, which like model serving is basically an extension of a microservice. And one way to describe this problem is with DevOps, which is a practice of trying to deliver the products safely, reliably, and quickly into production. It emphasizes source code versioning, automation, monitoring, stuff like that. And basically MLOps, or like most of this stuff is applicable to machine learning development, but there are some specificities that need to be addressed. One way to address it is with new buzzword, machine learning operations, MLOps. And most of it comes from the fact that the ever-changing environment in which the system exists is integral part of the machine learning as it is. So maybe the punchline, it worked on my machine, maybe viewed as it worked on my dataset, or it worked in Jupyter, or more production-oriented, like ML-specific, it worked on yesterday's data. Almost everything can be described in software engineering with the life cycle, and it's an apt analogy also here. By definition, machine learning, or AI in general, is like a living creature which takes input from its environment, it processes it, adapts to it, and hopefully it performs better after it. It also can be applied to the process of development of these systems. We take inputs to the experimental phase, we create a model, we see the results in production, and then we feed back this result back to the experimental phase. So what the phases can be. As in the first example, it all starts with the experimental phase. We're not trying to limit the freedom of experimentation, but we need to bring some barriers or guardrails that will enforce the reproducibility of the experiments. We want to track what worked, what did not, and we want to emphasize code reusability. So we just don't want to throw away all the code, but we want to find the path and archive or delete the stuff that did not work, and package the stuff that worked. Basically CI and CD for the code of the experimentations. When it comes to data, we want to provide environments for safe exploratory data analysis. So we want to create an environment where data scientists can design the models that can be then reproduced in the production. We want to limit the use of frozen datasets that may cause troubles later on in the production. One of the specific issues here is training serving skew, which describes the same thing, that the stuff that happened, or the data that were in the training do not match the data in the serving. One of the ways how to evade it is to supply generic transformations and pipelines that can be used in training and also during the serving. One of the newer concepts here is feature store, which has some narrower, some wider definitions. Basically, it tries to package all these issues and solutions to them into one place. So, for example, it tries to unify the access to the features during the training and serving, which is the issue of training skew, and then also it usually provides some like feature catalog that is quite useful for feature sharing, reusing the features one created, and like creating like a documentation. One of the cool things also that it usually supports something like a point-in-time correctness join, which is quite useful when you're joining the data sets of multiple data sources. As with any other abstraction, it brings its overhead. So most of the time you need a use case wide enough, so it's worth the time. Okay, at the end of the experimental phase, you have some guidelines, some documentations, you have verified which data work and which models are useful, model technologies. You have also some code base that can be used and refactor unit tested and so on. So you want to deploy all of this to the production. Usually the way is to ensure a repeatable build or training of the model, which is usually with some training pipeline, which can be deployed into production, and which basically a spot where you can adapt to the changes from the environment. Meaning that you don't have a static model deployed to production, which is usually not enough, but you have like an artifact of the pipeline. And for example, if there is some if you notice the degradation of the model performance, you can trigger the retraining and create a new model with hopefully better performance. There are many ways how to do it. One is with some performance-based metric that triggers the retraining, or you can basically train it each day, each week, each month, and so on. Once you have a model trained, you want to provide it to the users. You can do it as in a batch mode, where you deploy the model into the Spark or into I don't know, your Flink job, something like that. But usually the way is to wrap it inside the service and provide it as a service, basically. There is nothing new. It's basically a microservice, and nowadays there are many generic runtimes that allow you to take almost any machine learning technology and plug the model in and put it on top of some cloud infrastructure. Yeah. So the model is up and running, which you know thanks to the monitoring. You can monitor on all levels of the infrastructure. More basic ones are like latencies, error rates at the serving time, but also the data-inspired monitoring is where you want to ensure that the data is complete, they are fresh enough, there are no missing values, and so on. One of the more ML-specific monitorings is the drift monitoring, where you basically try to get the information whether the model performance is up to date. You can do it by monitoring its input or the model itself or the predictions, where you want to find out whether the how it was trained still applies to the production. So on the example of the data drift, which is named for the monitoring of the features at the input of the training, you want to monitor the current features, how they are in the real time during the serving or on daily basis, and whether that distribution of the features changed from the distribution of the training features. If it did, you want to maybe trigger the retraining, so the model is trained on the new data distribution, basically. You can also feed all this information you gained from the model outputs back to the experimental phase, and you can design new features, new models, may inform your decisions about new products in general. Yeah. So how you piece the pieces together, how you solve this puzzle is basically up to you, based on your use case. In our case, we have quite a wide use case, meaning that we have several products that implement machine learning, and also hundreds of models deployed into production. Also, as mentioned on the first slides, the scale is quite big, which determines the technologies we can actually use. On the other hand, most of the prediction that we serve are not needed in real time. It's just in near real time or asynchronously. So that means that we can sacrifice some latencies for the sake of more generic or abstract solutions that may help us implement stuff quicker. Yeah. So we definitely deal with big data. Usually the Kafka Hadoop file system or S3 compatible storages are the backbone of the raw data storages. On top of it, we have Spark and Flink jobs doing the transformations, and usually for the feature-specific storages, we use ClickHouse, and also we consider our use case quite wide enough to use a feast feature store. For model training, we use platform Kubeflow, and we use it. Actually, we are experimenting nowadays also with its Jupyter Notebooks environment paired with Elira to bridge the gap between the experimentation and production. So it's as small as responsibly possible. And also we track all the model artifacts and experiments in the MLflow, which can be nicely paired with KServe provided by Kubeflow for the implementations of model servers and services, which is on top of the Kubernetes, so we can access the resources from the Kubernetes and all the stuff that it provides. I have to also mention that we're far from only team at Seznam who deals with machine learning. There are many different use cases. There are teams or products that necessitate much lower latencies, for example. And in that case, there need to be implemented more custom-made solutions. But most of the concepts or tool may be applicable also in other use cases. For example, the LLM model servings happen to be on top of the KServe and Kubernetes with all of its GPUs. Okay. To bring it to the finish line, as one famous machine learning engineer said, one doesn't simply deploy a model without tools and practices that allow free and reproducible experimentation, support reliable model deployment, and monitor everything along the way. One of the more overlooked aspects are the people. As with DevOps, which try to connect dev and ops people, here it is mostly between developers and machine learning researchers or data scientists that need to communicate together and educate each other about the intricacies of the development of these systems. Okay, that's all. Thank you very much. Okay, we go to the questions. Okay, how do you recommend getting involved in AI and ML? What resources or courses are worth taking for a computer science student? Okay, great question. There are many resources, so I think the problem is to find the good ones, or find your path in it. Actually, once I asked the same question of our researchers, and they recommended me. There's I don't want to make an ad for the competition, but there is a good Google Doc or a Google website for with the information about ML, machine learning, from the more researchy stuff to the more engineering stuff. So, for example, that comes to my mind. Yeah. How do you handle data versioning for ML pipelines? Okay. Any tools which you'd recommend? Yeah. Oh, that is a great question. That is very problematic, I would say. Yeah. As I mentioned, we use Feast, feature store, and there is no versioning inbuilt. So we built some POC type stuff above it, and we use that. But yeah, it's quite hard problem, I would say. Don't you use cloud for your ML environment? Yeah. Yeah, we use Kubernetes. We run basically all of it on top of Kubernetes. I think there are some pipelines, Spark pipelines, then that still run on top of Hadoop, and also like you have computation engines like ClickHouse. This is basically like almost like a cloud that can compute. But for model serving, it's Kubernetes. For model training, if it's not meant to be like a parallelized job, it's probably still Kubernetes. Okay. I would say that's all. Thank you very much.